I can see it on here. There, you want to see? Oh, gee. Okay, well, at any rate, when we went to get samples of granite, we were able to get samples from a coring that was done near Los Alamos National Labs that they had done in a geothermal hole. And we had samples in granite all the way down to 4,000 meters. That's about 12,000 feet down in the ground. This is actually data that, again, Robert Gentry had originally obtained. And as a function of depth, the sample was at different depths. Here you can see samples 1 through 5 and the depths of them in meters down to almost 4,000 meters, which is 12,000 feet. And the temperature increases as you go down, and therefore the helium that's produced in this granite by the radioactive decay will tend to diffuse a lot faster at hotter temperatures. Up near the surface, we found that, and it's actually 1,000 meters below the surface, that's 3,000 feet down the ground, so it's not right at the surface. The temperature there is already over the boiling point of water in this rock formation, and up to 58% of the helium that would have been produced in 1.5 billion years of radioactive decay was still in the rocks. And yet, very simple calculations based on measurements, very tentative measurements in similar type rocks, would lead us to believe there should have been no helium at all. It would have diffused out much more rapidly, and there should not have been any helium left at all. Even down deep in the sample where the temperature was almost 300 degrees centigrade, there was still up to 0.1% of the amount of helium. Now that doesn't sound like a lot, but it is actually, given the diffusion rates. Well, we plotted this information, a variable called diffusivity. It's a measure of how fast the helium diffuses out through the minerals and the rocks, and this is a logarithmic scale. And I'm not going to go into all the units there, but it's plotted as a function of temperature, and it's in the reverse direction. So it's cooler over here, 100 degrees centigrade, and warmer to the left. This is called an Arrhenius plot. The reason it's plotted this way, it's traditionally plotted this way in the literature, so it's a little hard to interpret, but it allows you to have straight lines on this kind of a diagram if it's plotted properly. Well, you notice up at the top here, well, let me start with the red diamonds. The red diamonds in both here and here are estimated diffusivities based upon the amount of helium that was found in those samples, not from a direct measurement of diffusivity, but based upon how much helium was there given a period of time. For example, for the uniformitarian model, the rock is estimated to be 1.5 billion years old. And if that was true, with the amount of helium that was there, you would get this kind of a curve on this diagram. If the rock was only 6,000 years old, which is a creationist number, then it would have been plotted up here, and this would have been something like 4 orders of magnitude or more, almost 5 orders of magnitude difference in the amount of diffusivity. An order of magnitude is a factor of 10. So 4 orders of magnitude would be 100,000 times difference in the amount of diffusivity, and it would have been a much faster rate for the creation model than the uniformitarian model. Well, then the question was, what is the actual diffusivity? How fast does the helium actually diffuse out of rock? Well, we sent it to a commercial laboratory, a university that you would be very familiar with, and had these samples of rock measured for how fast helium diffuses out of the rock as a function of temperature. That's the blue data that we see up here. And notice how well the data flows and matches right up with the creation data that we had from the Gentry information. So we had actually predicted this curve based on the data we got from Gentry, saying this is where we expected it to be, and that's exactly where it fell with a 6,000-year model. Now, we're not talking about a factor of 2 or 3. We're talking about a factor of 100,000 difference between these two, so there's got to be something seriously wrong with the way in which this was done. So now we have an alternative method for estimating how old the rocks are. The standard method is how fast uranium will decay into lead based upon the observed decay rates that we have today. Now we have a new method based upon the rate at which helium diffuses out of the rocks once it's formed. Okay, all right, thank you. Whew. Okay, now what we have here is 2 hourglasses. The one on the left is representing the uranium converting into lead. The upper hourglass and the lower is lead. The right hourglass is helium. We're going to fill the upper part of the hourglass with helium on the right, and it's going to be running down into the lower part, and that represents diffusion, actually. We're suggesting that at some time in the history, you notice the little lever on the left there? It was turned on so that the uranium decay was accelerated, so that there was a tremendously high rate of uranium being converted into lead at various times, probably during the flood, maybe during the first 3 days of creation. At that time, it's producing a tremendous amount of helium, you see up here in the top, going across and filling this upper part of this hourglass, but it's coming down into the lower hourglass is diffusion, not affected by that accelerated decay. Over here now, at some point, the accelerated decay was reduced back to its normal rate that we observe today. Very little helium at all being produced, but there's a residual amount of helium that was put into the rocks, into the zircons and the granite, and this diffusion rate continued at the rate that we observe today, continued at all time. It was not changed by this change in accelerated decay over here. Now down at the bottom here, you'll notice that there are times so that during this process, today it shows 1.5 billion years, where over here on the helium, because it did not change, it shows on the order of 6,000 years, because it stayed at the same rate. Now, we should have more confidence in the diffusion rates because it was not changed by that process. Whatever process caused the decay processes to change rates, it did not affect the rate of diffusion through the zircons. Okay, now then, let's see what happens. Oh, good. That's a little unnerving, you know. Okay, that was the basic, and I'll come back and summarize that a little bit more. Another project that we worked on was with Dr. Snelling, and he dealt with some radio halos that have all kinds of evidence for accelerated decay. We collected rock samples, granite samples from all over the world. This is Stone Mountain in Georgia and Grand Canyon. I went with Dr. Snelling on this particular trip, and I have to warn you, never be a geologist assistant. Because we started at Glacier Point in Yellowstone and walked down through the canyon about 6 miles, and by the time we got to the bottom, I had 50 pounds of rocks in my backpack, and he was carrying the GPS. Anyway, we collected rocks from Yosemite, from Stone Mountain, from places in New Hampshire, in Norway and Sweden, in Australia, various places around the world. We had something like 1,000 samples in which we were looking at radio halos. Now, a radio halo is a little defect in the rock that's produced by the decay of the uranium or other radioactive materials. As it sends out these alpha particles, in addition to producing the helium in there, it also damages the crystal structure and leaves defects or a discolored region in the rock, and it produces this radio halo effect. Now, here's let's see here, how do I do this? Okay, this is a zircon showing kind of how this happens. These are all alpha particles emanating from the zircon, and it actually goes out into surrounding biotite that surrounds the zircon, produces this kind of an effect, and in biotite, which is a kind of a mica, it has layers of the mica so that you can actually peel it off one layer at a time so that you can get to the point where you're right at a level where the zircon itself is, and you can see rings. That's why they're called halos. It's actually a spherical shell of damage, but when you peel it off in the right direction, you get these little surrounding circles called radio halos. The radio halos are actually in these black specks. If you've seen granite, the little black specks is the biotite. In that biotite is where the zircons are located, and the damage occurs in there. And in a process of producing the decay from uranium to lead, there's intermediate chains of material like radon and polonium. Here's the polonium halos, and because of water moving through the granite during this process, the polonium halos, the polonium particles are moved down flow from the uranium, and you get these little polonium radio halos displaced from where the uranium is. Now, the importance of this whole issue is that it takes millions of these decays from the polonium center to produce